now it's time to start. I introduced next speaker, Rachid EL Maaouy. You can share your slide, please.
Okay, good afternoon, everyone. My name is Rachid EL Maaouy. I am a PhD student. I'm going to talk in this presentation about part of my work called relative Gorenstein flat model structures. So this presentation will be divided into three parts. First, I'm going to talk about abelian model structures. Then I'm going to illustrate with an application called the GC flat model structure. Then I will conclude with some references. So model categories were introduced by Quillen in 1967. The motivation behind such introduction is that their utility in solving the localizing problem for categories. So let's talk about this problem a little bit. Let us fix category A. For example, you can think of the category of modules over a ring, chain complexes, or the category of topological spaces. And let's fix a class W of morphism in this category. So the localizing problem is to investigate if we can treat the class of morphism, the morphisms in the class W as isomorphism. So we can do this. In fact, we can construct a category in which the morphisms in class W are becoming isomorphism. But of course, there are some complications, and working with this, let's say, a category is somehow difficult. However, if we work with model structures, we will not find such difficulties. So what is a model structure? A model structure over a big complete category is simply three classes of morphisms: cofibrations, weak equivalences, and fibrations, satisfying some axioms. And with these axioms, we can construct a new category called the homotopy category. And inside this category, every morphism from the class W, or what is called here weak equivalences, is an isomorphism. However, in this talk, we are interested in more particular instance of model structures called abelian model structure. They were introduced by Hovey in 2002. They are model structure in the sense of Quillen, but with the following extra assumptions. The following assumption is a cofibration is or coincides with monomorphism with cofibrant co-kernel. And here we mean by cofibrant object is an object such that the unique morphism going from the unique morphism 0 to X is a cofibration. And for the dual notion is called fibration. And it coincides with epimorphism with fibrant kernel. And here, fibrant kernel or fibrant object in general is an object such that the unique morphism going from that object to the 0 is a fibration. And looking at this definition, we can see that because in a category we have objects and we have morphisms, and looking at this definition, we can see that we can shift all attention from morphism to objects. And this means that we can forget about morphism and focus only on objects. So this brings us to what is well known now as Hovey's correspondence. This result means that there is a connection between model structure and some classes that satisfy some properties. And I will talk now about these properties. First, we need to know what is a cotorsion pair. So a cotorsion pair is a pair of classes of objects in an abelian category, X, Y, such that X is the left orthogonal of Y and Y is the right orthogonal of X. And the orthogonality here by means of the X functor, the first X functor. And this cotorsion pair is called complete. F for any object A in this category that we work in, we can find two short exact sequences with the following form. And the final notion is the hereditary property. So a cotortion pair is called hereditary if the class X and Y are orthogonal not only for the first X, but for all of them starting from 1. And with these definitions, we can state the Hovey correspondence. So Hovey correspondence states that there is a one-to-one correspondence between abelian model structure from one hand and a triple of classes Q, W, and R such that the following two properties hold. So the first one is that the following two cotortion or the following two pairs are complete cotortion pairs. The second property is that the middle class in such triple is thick, and this means that this class is closed in their extensions, kernel of epimorphism, co-kernels of monomorphism, and direct sum. So when we come to reality or real objects in practice, I mean, the difficult part is finding this class W. So because in general, it is not obvious. We often know the class Q, we know something about the class R, but we don't know the class W. So there is another result that we need to recall is the following. It states that even if we don't have such class, we can assure its existence. So if we have two complete and hereditary cotortion pairs such that the first component of the first cotortion pair is inside the first component in the second cotortion pair, and the second assumption is that we have compatibility between the two cotortion pairs. So if we have two complete cotortion pairs with the following two properties, then there exists a unique class W such that we have an abelian model structure. Now we recall everything we need in order to apply to our main concept next. So now we talk about our application. First, we need to fix a setting that we work with, and so for simplicity, we fix R to be a commutative Noetherian ring, C to be a semidualizing module. Here, semidualizing module means that C is finitely generated, such that the ring R is naturally or canonically isomorphic to the endomorphism ring of C. Before talking about the main concept, we recall two other concepts that we will need next. A module N is called IC plus injective if it is isomorphic to direct summand of direct product of copies of the character C plus, or we can simply say it is a relative injective. The second notion is relative flat. So a module is called if C flat or simply relative flat if its character module M plus is relative injective. And during this talk, we used the notation FCR to denote the class of flat R modules. So now we are ready to talk about the main concept of this presentation. So an R module M is said to be Schisse flat if there exists an exact sequence F such that the module that we are talking about is the image of this morphism. Modules on the left are flat and modules on the right are relative flat, and such that if we apply the factor E tensor bar to this exact sequence, we still get an exact sequence. And throughout this talk, we use the notation GC flat of R to denote the class of GC flat modules. So the aim of this talk is to show that there exists, or before that, so the question is that we want to answer is that there exists a module structure such that the first component is the class of GC flat modules. And this is, in fact, the goal of this talk, to show that there exists such a triple. So using the previous theorem of GSP, we can assure the existence of such class W. So we only need to talk or discuss the following two properties. First, we need to prove that the class of GC flat modules is the first component of a complete hereditary quotation pair. The second part, which is the difficult one, is it is difficult because we need first to find the class R, because we know nothing about R, and we need to prove that it satisfies the following three properties. So in order to apply GSP theorem, so a natural choice for the class R is to define modules as the right orthogonal of relative flat. So a module M is said to be system quotation or simply relative quotation if it is right orthogonal with respect to the first X to all relative flat modules. However, this choice is natural, but the problem is that this pair is not a quotation pair in general, unless the rank R is relative flat, but this is not the case in general. However, we can keep this class, but with the help of another class, we can overcome this problem. So we use the well-known class of bus class to solve this problem, but let's recall it first. So the bus class, denoted as PC of R, is a class of modules satisfying the following three properties. And with this class and the previous one, we define a new quotation module called HC quotation, or simply, again, relative quotation module if it belongs to the intersection of the following classes. So now we can see that we have the class R well identified. So now we can apply the previous theorem of GSP in order to get our model structure. First, we have the main result stating that the class of GC flat modules is the first hand side of a complete and hereditary quotation pair. For what is related to the class of R, we need only to recall one concept that we will need is the relative flat. So, and we define a module to be relative flat if it is right orthogonal to all relative quotation modules. And we use this class to denote the class of such modules. And the first property we have is that every relative flat module is GC flat. The second property is that this class of relative flat is the left-hand side of a complete and hereditary quotation pair. And the last property that we need in order to apply GSP theorem is the compatibility between the GC flat quotation pair and the relative flat module quotation pair. So with all these in mind, we are in a position to state our main result, which state that there exists a unique ABM model structure on the category of modules such that the first component is the class of GC flat modules. The third class is the class of relative quotation modules, and W exists because the previous theorem. So we can see that we have solved a problem, but another problem arises here, because when we come to abelian structure on homotopical algebra in general, this class W is the most important class, because this class determines the homotopy category of this model structure. So this is an open question that we are still working on, and this is the last thing I'm going to talk about. Here are some references that I have used during this talk. So thank you so much for your attention.